So now you all are now very familiar about our activities of Civil Engineering Sectional Committee, and you know me, I'm Kamala Gurunathan again. So I reserve the time without explaining about our activities this time. However, we appreciate your participation and the keen interest to participate in this program, and please keep it up. So today's webinar is under the title Three-Dimensional Modeling under Medium-Rise Buildings, Designs and Constructions by Professor Dishan Jai Singha, and it is the 11th lecture of the series. Anybody, if you want to see the, get to know the previous lessons and the previous lectures, you can type ISL Media in the YouTube, and you can reach all the programs or webinars done so far. So those who missed the lectures, you can refer that way. We'll start the today's event right now, and Professor is ready, and I will invite our eminent personality who is continuously sharing his knowledge with our members, and that is he has taken the challenge of giving you the best knowledge, know-how about all buildings, designs and constructions. Without further ado, stage is to you, Professor Dishan Jai Singha.
Thank you very much. Thank you.
Civil Engineering at the University of Moratu, as well as our chairman of the Civil Engineering Sectional Committee. So please proceed.
Thank you very much. Thank you very much, Engineer Kamala.
Welcome.
So today I'm going to talk about the modeling part. How do you think about modeling? So for that, I will take a very simple example initially. So I'll take a building having frames like this. Then let's say we are going to have a central core like this, and we are going to have columns at these locations. Now these are simple structure that we can model in many ways. So first thing you have to understand is, what is computer modeling? What is the purpose of computer modeling? We like to see the bending moments, shear forces, axial forces, torsional moments, deflections, and also sometimes long-term behaviors like construction sequence effects. And when you do very advanced things, you like to see creep, shrinkage, effects, so many different effects. So in early days, many engineers would have been very happy if they can find the bending moments, shear forces, axial forces, sometimes torsional moments also, and probably deflections using some method. So in early days, we developed manual methods, many manual methods. In 1964 to 1970, we saw the development of computer methods. And 1970 to 1990, we saw a huge development of finite element method. finite element method. So when this was, during this era, we tried to do many things 2D, two-dimensional. And before this era, before 1970, or even you can say 1980, or even close to 1990, most of the analysis was done manually. So you learn slope deflection method, moment distribution method, then approximate methods, all kinds of methods. So before 1990, we did many things manually. But the real development took place in 1964 to 1970, but it did not take up that well. So you'll ask, what is the reason? The reason is we had to work on, so even 1990, many people working on mainframes, computers. Only in somewhere around 1985, we got IBM manufacturing some computers with very low capacity, like 1 megabyte RAM. Random access memory was only about 1 megabyte, very small. And somewhere around 1990, we saw 386 machines with about 4 megabytes of RAMs. And somewhere around, after that it started, somewhere around 1994, 95, we saw a machine called Pentium coming. And today it has developed so much. You have i7s with 64 GB RAM. And then you can have 1 terabyte hard disk, 1 tera hard disk, enormous computer power. So basically the main bottleneck was not the technique, but the computer capacity, the accessibility to computers. But today things have changed a lot. And recently one of my friends, we have a chat channel, and one of my good friends has indicated that a person with just little above the average intelligence can design a 100 to 200 story building. But sadly he's mistaken, because when you exceed 40 to 50 story, you need very special skills to design. So basically I will show you the skills that you need, because I have solved the main bottleneck that we had going beyond 110 floors. And now we have with that solution, now we can go anything up to 200 story buildings easily. And these days, one of your lecturers of this series, Dr. Dhammika Maharachi of Robert Bird, Australia, Brisbane, Australia. He did 120 story, the tallest in Malaysia. It's already constructed. Now he is doing the further modeling on this technique to see, how to build 140 story with 1 hectare footprint at 140th floor. If you look at very tall buildings like Burj Khalifa, they all go like this. Even CESC Tower goes to 104, but it goes like this. And then even these 1 kilometer tall tower, the area at the top is very small. But we don't want that. They are useless buildings, although they are told there's nothing to occupy. We like our buildings to be like this. For that, we might make it even bigger, but we don't want any reduction. And for that, I have actually developed a method where you can kill the wind. I developed a method where you can kill the wind effects, because we know how we started our course, our series. We started saying tall buildings are subjected to lateral loads. If we can say tall buildings are not subjected to lateral loads, tall buildings are not subjected to vortex shedding, then we have won the war. We have cracked the nut. So basically, I have developed a method to do that. And now we are in the process of checking the viability of the method, where you don't design the building for wind loads, you design the building only for vertical loads. But of course, you have to have very strong lateral load resisting systems, not to resist the wind loads, but to ensure the building has stability. Because buildings can buckle and fail under their own weight. So we have to make sure when you have a very tall building, the tall building will not buckle and fail under its own weight. So that is the main task. And how do you assure that the building will not fail under its own weight? And for that, we have to ensure we go for super strong materials. So what is the super strong material? Steel or concrete? The material is concrete. Why? It has E constant, and that is 200 kilonewtons per millimeter square. It does not change. Concrete, we make from 20 megapascal, we go up to 100 megapascal, 90 megapascal. I'm talking about cylinder strength. Otherwise, in cube strength, we go from 25 megapascal up to 105 megapascal in Eurocodes. There's a table on one of the pages, the early pages, close to the beginning of the code, that gives all the properties. And you see, what happens is, when you have 25 megapascal cube strength, the E value is about 25 kilonewtons per millimeter squared. And at this end, you might reach something close to 45 to 50 kilonewtons per millimeter squared. And sometimes, you might use 150 megapascal concrete. And you might use it not for strength, but for very high E value, very high E value. So you can see the scope is not something like this, it's huge. So for that, you have to read. The first read mostly Manji, then read McGinley, then if possible, you can also read, this is an old book, very old book, Hong and Evans, written for BS 8110. It's a very useful book to understand the theory of concrete, the theory behind concrete. You can read that also. It's not a new version. It has, because Professor Hong is a very old man. Even I met him in 1994. Even then, he was a fairly old person. Now it is nearly 30 years gone, and I don't think he's living anymore. Maybe he's not living. Maybe. I'm not very sure. But, he's a great person. He has written this book, The Concrete, I can't remember the exact name of the book, but you can just type Kong and Evans on www, and I'm sure you can download from some source. It's an old book, but it tells you a lot about concrete. So the moment you understand how the concrete behaves, it's very easy for you to stretch it to its limits. And if you don't have that kind of understanding, every time you try to do something, you feel, okay, will it work? Will it work? You will be asking this question, will it work? That's a bad question to ask, because you are not sure. So when you are not sure, you ask this question, will it work? Will it work? Will it work? And then you might think, okay, why should I take all these unnecessary risks? I'm not going to do it. That is not the correct way. Correct way is, what you have to understand is, we are Sri Lankans, and also members of ISL, one or other kind. That means, you all have passed GC advanced level, very competitive examination. You got through one way or the other. That means you are all brainy. Very brainy people. So use it. Now to use it. Use the brain when your tummy is empty. Brain has rested. Two important things. Why? You have a person, his tummy is full of rice. So which direction the blood moves? Or the blood will move to the stomach, no blood to the brain. The stomach is empty, no rice in it. The blood will move there, but brain is tired. Then you have a sleep, 4 to 6 hours, maybe. 4 to 6 hours. Get up. What is the situation? Nothing here. Nothing here. It's fresh, huge but supply here. Then you have a super brain. Do things when you have a super brain. That means sleep early, get up early, do not eat but drink water, and then start working. Then your brain will become a super brain, and do work at a time that your brain is super brain. This is not what our young generation is doing today. Everybody thinks, go to work, get up at 6, work at 8. You go to work after a big pot of rice, big plate of rice, sleep at workplace. Then for lunch, another big thing. Again, like sleeping, because all the blood is in the stomach. Then come home, work until midnight. So by the time you come home, you had enough problems because you are feeling sleepy all the time. So your workplace is full of problems. So you come home as a tired man. Now you try to learn something. It's a total flop because you are trying to use a very tired brain after a good meal for dinner to work. It will never work. So it's a wrong method. And in the ancient times, we said, eat like a king, eat like a prince, eat like a beggar. This dinner. Then early to bed, rise early. This is what we said earlier. So we had students getting up at 4 o'clock every day, work until 5:30, leave home by 6 a.m., take the school bus or walk or cycle to the school, and by 7 a.m. you're at the school. Then you will be asked to stand under the sun for half an hour, and that is to get vitamin D. And when you have vitamin D, you will have high calcium absorption. So you have high calcium absorption, and with that, what will happen is you'll have a good immunity system, good immunity, and then sometimes they even play before the school starts. So now a very active person, and they concentrate, and by 1:30 school is over. By 2:30 kid is at home and no tuition. Sometimes he might sleep a little bit, and evening playing and some schoolwork, not a lot. Sleep early, get up early, study early in the morning, and they had a super brain. So we had top class engineers like Rampala, Vimala Surendra, E.O.E. Pereira, Gomez, A.N.S. Kulasinga. We had super brains. They did so many things. And you can see the reason. The reason is they ensured they are active, their brains are working, and most of them worked at the time where brain is willing to work. And today it has all changed. Everybody is, very keen on mobile phones, computers, and internet, and it's hard to find a person who sleeps before 11 p.m. So if I want to organize any ISL activity, I have no fear of giving a phone call at 10:30 p.m. if I am still not sleeping. And most of the days I sleep from 5:30 to 6 p.m. until 9:30 p.m. So after a good rest, I can do many things. And then, so this is about 3 hours, and then I sleep another 2 hours from about 2 p.m. to about 4 p.m. And then again start working at 4 p.m. And so you can see I can crack difficult problems. I can tell you one story. And that was, I was, one day I was asked around 5:30 p.m. that, I had to get a solution for this Nigamo hospital. And my task is 50,000 square feet in 2 months at rupees 3,500 per square foot. So you can see 50,000 square feet in 2 months at rupees 3,500 per square foot, where the land is available. So when I was asked this problem, and I was asked to come for a meeting at 10 o'clock, 10 a.m. at Ministry of Health. Ministry of Health. Because we have we have given an evacuation order saying that the main building is not in good shape, so you have to evacuate. And then they found that they have no place to evacuate, so they asked me, okay, to come up with a solution. So it was 5:30 p.m. and do you know what I did? I had an early dinner. At 7 p.m., I slept until 2 p.m. So when I got up at 2 p.m., what did I have? I have empty stomach and fresh brain, and blood is pumping from the heart only in one direction, that is to the brain. So brain is getting enough oxygen, enough energy. So I started a design at 2 a.m. and by 6 a.m. I have done a design for a 2-story building with a portal frame and 20-meter span. The complete design was completed. A methodology was found to reach 3,500 rupees per square foot, where those days, 2015, you know the costs. The minimum cost is 6,000 to 7,000 rupees, and I had to do it at half price. So I came up with a solution, and then later we completed this. A building complex like this, because doctors wanted, instead of 20 meters, they want 15 meters. And in addition to that, we did this also. We did a 3-story building as well, and then gave 58,000 square feet for 200 million. 58,000 square feet for 200 million rupees. So what I'm trying to say is, if you want to be a good engineer who can take the maximum advantage of all we are offering today, change your habits, because most of you are lethargic, can't take rational decisions. You have fear of taking decisions. So many things happen because you have wrong habits. You have wrong habits. You have wrong habits. And then today we are facing huge dollar crisis. And do you know what is the reason? The reason is trying to sell rice at rupees 100, 220. That is the reason. Why? Because when rice is cheap, we eat a lot for breakfast, we eat a lot for lunch, and we eat a significant amount for dinner. And today, our population is overweight. We don't have a proper body mass index. And everybody is on the upper side of the body mass index. We have non-communicable diseases like diabetes, heart problems, high pressure, high cholesterol, then high triglycerides, and all the people are like this, all have a big tummy, majority, and the life expectancy of 60 to 70 years. By that time, if you want to go beyond that, you have to be really lucky because we had all the problems and so. So basically, just think that we are going to change these habits and make ourselves a knowledgeable nation. So let's see how we think about this mathematical modeling or 3D modeling in a logical way. So what is now this is the building, and if I'm making a model of the building, if I'm making a model of the building, if I say I'm going to make a model of the building, what is the meaning of that? The meaning is I'm going to come up with a mathematical model. And what I'm simulating is loading behavior. And so basically, we are doing mathematical model of the structure. This is our structure, and what we are interested in simulating the loading and finding the behavior. Behavior will be the response of the structure, like bending moments, shear forces, torsional moments, bending moments, shear forces, torsional moments, axial loads, and so on. And then we are also interested in finding deflection. That's what we are interested in. So if I'm interested in this, simulating the simulation of loading and the behavior, if I look at this building, I can say it's a non-twisting building. It's a non-twisting building. And I apply loads in Y direction and X direction. It's a symmetrical building. Symmetrical buildings cannot twist due to lateral loads. So it is non-twisting. And if you look at the shear walls, you might say it's proportionate as well. And I explained, what is meant by, I took 4 lectures to teach you about the structural forms. So I taught you about the shear wall buildings, and I taught you about the non-twisting buildings, twisting buildings, proportional shear walls, and non-proportional shear walls. And I explained 4 combinations. And I told you if the structure is proportionate, non-twisting, that means the member sizes are more or less the same, or if they're changing the same way, that means proportionate, and it's not twisting, it's a symmetrical building, or even if it's not symmetrical, still not twisting because the shear center coincides with the geometric setting. Under such a situation, you can convert the 3D structure to a 2D structure. And what we can do is we can lump. Now let's say these columns are 400 by 400. I can lump the columns and I can create one frame. Create one frame and 4 columns. And get this. And the size of the column is like this, 1600 by 400. The size of the column is like that. The axis of bending is, main axis of bending is this. Main axis of bending is this. Because I have lumped four frames to become one. And let's say these walls are 250 millimeters. And you might ask why I select 250 millimeters. 250 millimeters can be cast very easily. You generally don't get segregation, all kinds of problems that you get in 200 millimeter walls. You don't get them in 250 millimeter walls because there's plenty of space. So generally, I prefer 250. But I have designed, from 160 onwards due to various requests. But now I have decided I'm not going to design anymore because it's a real pain in the neck when it comes to the construction, because the contractors struggle a lot when the walls are less than 250. And our walls are very important structures or structural elements. And why do you want to struggle a lot and put the contractor in deep trouble by selecting very thin structures where there's no way? And in one of the magazines I saw, there was an inexperienced design engineer, and the guys at the site saying, "Can you please send us some teaspoons to pour concrete? Because there's no space to pour with showers." So they were asking for teaspoons to pour concrete because there's so much congestion of reinforcement in the structure. And if you see any congestion of reinforcement in the structure, it is an indication that the design engineer has not designed a reinforced concrete structure. He had designed a steel structure covered by concrete. So never ever design steel structures covered by concrete, because if you put a lot of reinforcement, there's something really wrong with the sizes you have selected. There's something really wrong with the size of the members you have selected for the grade selected by you. Because always make sure the reinforcement use is reasonable or minimum. And if you have a lot of reinforcement in a structure, we call it a structure. It's a steel structure, but covered by concrete, because even to carry bending, you have doubly reinforced section. Doubly reinforced section means we are using very expensive steel to carry bending when we could have easily carried the same moment by selecting a larger section where very cheap concrete will carry compression, and only the tension is carried by steel. But because we have a deep section and a large section, now the reinforcement requirement is very low. On the other hand, if you think there are severe restrictions on the depth of the structure, then don't use reinforced concrete, go for pre-stressed concrete. And if you see a design engineer using a highly congested beam, then there's something really wrong in that design. And in my case, I always make sure the structures I design are primarily singly reinforced. And I hate to see a structure needing doubly reinforced beams, because what I do is, if I can't handle with singly reinforced, and the depth of the structure is, depth of the beam is limited, what I do is I increase the width. I increase the width. So if I have a beam which is extremely congested with so much steel, very simple. Make it wider. Make it wider. It is not the most efficient way of improving the section, but if the depth is restricted, you can't increase the depth, increase the width and make it lightly reinforced. Because when you have plenty of concrete area, can actually reduce the compression steel. But you cannot actually reduce the tension steel. That cannot be done. It's difficult to reduce it. But at least you can reduce the compression steel. And if at all possible, make it wider and deeper. The moment you do that, you can reduce the compression steel, you can get rid of compression steel, you can reduce the tension steel. And why I say this is, in today's context, the price of concrete is 22 to 23,000 rupees per meter cube, and steel is 70,000 to 400,000 because of this very high steel prices. Even the wastage is costly. Wastage is costly. So steel prices are in this range, very expensive, because if the steel prices are cheap, then the wastage is also cheap, because we cannot use 100% of steel. Some wastage is there because we have to cut the steel and do various things. So there's wastage, but because steel is about 250,000 a ton, the wastage is very expensive, and because of that reason, you can see today a contractor has to use 400,000 rupees per ton if they want to really do it profitably. I mean, sometimes some might quote 370,000, but they struggle a lot. And again, I hate these people, quoting less and making a real mess. Because the moment you quote very little, your profits margins will be thin. The moment the profits are thin, the contractor will start struggling to deliver. Then he has to cut corners, sacrifice the quality, and at the end of the day, client is a loser. So this award in contracts for the lowest sum is not the best. You must always go for a reasonable sum and a good contractor. Then the contractor will be happy, client will be happy, the consultant will be happy, and above all, the users will be happy. Otherwise, users will have very bad business. So again, now we see all these members will deflect by the same amount. So what we can do is we can represent the wall like this, wall like that, and this will be a wall of say 6 meters of length and 500 millimeters of width. Why? I have lumped two walls together. So 500 is the width, and this is 6 meters. That is 6 meters. So length of the wall is 6 meters. So what I do is, now I have to ensure the behavior is properly ensured. So for that, I have to make sure that there's a link between these, but there's no moment transfer because these are connected only by the slab. So basically we can't have a moment transfer. So what I do is I'll have a connection through the member. Right. Now if I'm having a finite element package, that allow me to model these as shell elements, it's fine. Let's assume that I don't have a shell element in it. So what shall I do? Then I can model this as a column located at the center, and then I will say the I value of the column is 1/12 into 500 into 6,000 cubed. 6,000 cubed. 1 into 1/12 into 500 into 6,000 cubed. So I'll have a single column. But I have to show that it has a width. So how can I show that it has a width? What I do is I'll have a 90-degree angle, a member, and that member is called a rigid arm. And how could I select the size of the rigid arm? Rigid arm will be something like, so I get the I value of a typical section, something like 600 millimeters deep and 400 millimeters wide. And what I do is I calculate the I value of this and then multiply it by 1,000. And then I can say it's a rigid arm because it has a huge rigidity and it does not deform under the normal forces because it has a huge rigidity and it's called a rigid arm. So what I do is I take a typical section, typical beam section, and I allocate that as the rigid arm, but I'll go to the set modifiers. All the programs have some option called set modifiers or specifying the value of second moment of area. What I do is I will define a very high second moment of area for the rigid arm. So even if I don't have shell elements in the program that I'm using, and I can easily model the structure. If you have a 15-story building, the modeling of the structure is very easy. You can model it in few minutes, and you don't need a sophisticated package like SAP 2000. And we model these structures by using, there was a small program written in Asian Institute of Technology, and they gave it to us almost free of charge because we were collaborating with them a lot, and it was called MicroFeep. And it was a DOS version program. It was called MicroFeep version 1 for buildings, version 2 for grillages. Again, all are 2D structures. And we also had a program called XCTabs, and XCTabs was something becoming, coming closer to ETABS program, XCTabs. But it was not a very good program because it didn't have good graphics. The graphical interface was actually generated by one of our students called Gunratna, who did his master's at AIT. So he got a first class, he did his master's at AIT, and he developed the graphical interface by using graphical routines of Fortran 77, the computer programming language they use for MicroFeep. So when I started teaching after my PhD in 1992 to the batch of there are a lot of engineers of that batch are structural engineers, and one is engineer Nirmali Jayakodi, or Nirmali Pereira or Jayakodi of State Engineering Corporation, and then engineer Samit Jayakodi, and there are so many other engineers of that batch. And I introduced them in MicroFeep 1 in 1992, and then we introduced that to many others later, because that was because those days the best machines that we had were 486 machines, so very small machines. So we used them, and then somewhere around 2005 only we introduced SAP 2000. So SAP 2000 was available only after 2005, And the first students to learn this in our university were like, the batch of Dr. Chintaka Mallikarachi and so on. The semester batch students had the chance of learning SAP 2000 those days. And today we have come a long way in modeling. So we don't think of doing this kind of model for a structure like this. But I want you to understand one thing. That is, just look at this structure. It has 4 frames, 4 main frames. These are just columns, and 2 shear walls. 2 shear walls. And the dominant direction for wind is y direction, because x direction is so small and it's a long structure. So the chances of the wind in x direction becoming predominant on this building is very small. Actually, the predominant wind direction is y direction. Y direction. Predominant wind direction is y direction. So we are really concerned about the behavior in y direction, but we'll check the wind in the x direction as well. There's no problem. We can check it. But we know just by looking at this structure, predominant direction for wind, critical wind is y direction. So we look at y direction, and then what we do is, now you look at the compare the model, and it's a mathematical model. It's not the structure. And we create a mathematical model. We can simulate the loading. So I can simulate the wind loading on this structure, because for vertical loads, I can analyze a simple subframe. I can analyze a simple subframe like this. And then fix it, but put this on rollers like that. Otherwise, you will get wrong answers. Put this on rollers like that. That because we don't have any deformation here. If we fix it, then it's a problematic, because then you'll be transferring the load upward direction. Fix it. So do this. And then we can have the loadings like this. I'll just draw the loadings, all loaded maximum. Then this is maximum, minimum, maximum, minimum, and then minimum, maximum, minimum, maximum. And then we'll also get another bending moment diagram from due to wind, and that can be obtained from the other one. That is, it will go on in direction. Yes, it will come like this, and like this. So you get a wind. So you have the bending moments due to vertical loads, and you have the bending moments due to horizontal loads. And you have to add these up, find the final bending moment ended up. It's a lot of calculations. So you have to design a beam, you need the vertical loads. To design a beam, you need the lateral loads. So lateral load moments will come from this model. Lateral load moments will come from this model. Vertical load moments will come from the simple subframe analysis. And then you combine them, get the final bending moment envelope, and then undertake what? Moment redistribution. Undertake moment redistribution. So once you undertake moment redistribution, why? And the reason is again simple, because if you look at the stress strain curve of concrete, takes a shape like this. Steel takes a shape like this. So if the strains are small, then the stress diagram is triangular. The strains are large, the strain, stress. the strain, then the stress diagram is like this. And he also is cracked, but here it's like this. So we can say rectangular parabolic. So reinforced concrete behaves as a plastic material. For a plastic material, you have to do a plastic analysis. And that is, you have to assume pins at all these locations and find which pin gives the moment. Very difficult to do for real structures. Very difficult. But this is the correct method, very difficult. So what we do is, we do elastic analysis. We do elastic analysis and get a bending moment diagram like this. And then we say, if you perform plastic analysis, we can actually reduce the moment here, reduce the moment here. And this reduction can be easily represented by change in the origin of the bending moment diagram. So if this is x, this value is also x. So if this original moment was m, now the design moment is m minus x. And similarly, you will find if this moment is m1, initially, now the design moment in the span is m1 plus x. So there's a logical thing to do. It's a logical thing to do. Why? It's a very logical thing to do because at this support, we have a rectangular section. In the span, we have a flange beam. A flange beam is very efficient in carrying bending moment. And is not so efficient. So what we do is, we try to like shedding the moment from not so efficient section to efficient section. So we can shed up to 10% in unbraced structures, and we can shed up to 30% in braced structures. And we know, because we are having shear walls, most of our structures are braced, so we can easily shed moments up to 30%, but the value that I prefer is 20%, because the design is very easy when you shed 15% or 20%. When you shed 30%, you have to be very careful with many calculations. Calculations become very tedious. So because of that, I like to shed about 20% moment. So again, there's a logic to this. If you have a beam like this, have a beam like that, then where can you get failure and cracks? Here you will not get any failure because it's supported. But where can you get failures? You get failures unless in the middle of the structure. If you don't get your shear calculations wrong, you might get a crack forming like that. But generally we can avoid it because we always must provide enough shear reinforcement. Then you'll ask why? Not only for shear, because all these plastic hinges form where? Or the plastic hinges form at the support. So if in an earthquake situation, where do you get plastic hinges forming? at the support. So I like up to a depth length of 600 millimeters. I do decides by using simple rules. I have a rule 75 millimeter for link spacing. And I use 8 millimeter QST bars, high strength bars, ductile bars. Why? My steel cannot provide enough confinement under earthquake situations. To provide enough confinement, you need high strength steel. So you must go for QST bars or QT bars, so 500 megapascal bars. Never use my steel of 250 megapascal. So I use 75. Then I will move to about 125 to 150 for about another 1 meter or so. After that only, I'll find the place where I can use nominal steel, and then I will use nominal steel in that region. So to ensure that all this work, when I select the sections, I make sure the shear stress simple V is 1.5, but never exceeds 2. The shear stress is about 1.5. You can get 1.7, 1.8, but never exceeds 2. When the shear stress is about 1.5, you can create a rule where you say T8 at 75 over 600 millimeters, T8 at 125 over another 1 meter or 1.5 meter, depending on the span of the beam, and rest T8 at 200, because shear failures cannot occur in the middle of the beam. Shear failures cannot occur in the middle of the beam, and Eurocode has created a real messy calculation for shear, and the idea is to select few reinforcement, and I don't care about it because I generally don't save in beams. I ensure that beams are over-designed at the correct location, not all the locations. I always ensure beams are over-designed at the center where the failures can occur. I'll make sure that beams are over-designed at the center where the failures can occur. I also make sure beams are over-designed at the support for shear. And I also again ensure that beams are provided with sufficient confinement in case that plastic hinges form in an earthquake lasting more than 20 seconds, then still the concrete is having sufficient confinement that will assure hinges form, but concrete will not crush. Why concrete does not crush is a lot of links can create a triaxial stress state. And in the case of a triaxial stress state, if you look at the stress moment curvature curve for concrete, normal concrete will go that moment curvature, and some confinement will do that. A lot of confinement will go to that. And I like this. That means I like a lot of confinement, so I go with some simple rule like T8 at 75, and then T8 at 125. After that, we are away from the earthquake zone, earthquake affected zone. We are away from the earthquake affected zone. So let's have a nominal reinforcement for shear. And then again, there are other locations. You have to be very careful, because when you have a main beam, we might have a situation like this. This is the main beam, and somewhere we have a secondary beam, and that comes, these are the places where I'm going to provide a lot of reinforcement. Now, the secondary beam is coming at a location where I have very little reinforcement, but I have to provide some additional links at the place where the secondary beam meets the main beam. So this is the secondary, this is the main. So again, keep in mind, shear links, low concentration of shear links in the center is valid only if second beams are not there. Second beams are not there. Because all these second beams are designed as simply supported. And in the case of a simply supported beam, you cannot have anything more than 2T10 or 2T12 at the top, because otherwise it will not be a simply supported beam. So you have a situation like this. So these are the main beams. So you have to provide some reinforcement at the top and anchored. If you provide a lot, then the main beam will go into torsion. It's wrong. So you can have any amount of reinforcement here. So you put some reinforcement at the bottom, but top is very small. So what you do is you can have a U bar out of T16. If you think the anchoring of the beam, anchoring of the second beam is very important, you can have U bars in the middle of the beam, because any U bar in the middle cannot create a hogging bending moment. So you can do, for connectivity, you can have U bars, T60 or T20, but don't provide a lot of reinforcement in the top, because they are designed as simply supported. So they must carry a maximum of T2, 2T12. But these days we don't call them T. In Eurocode, we call them 2H10 or 2H12. And we use H16 or H20. H16 or H20 to anchor the second beam to the primary beam. So these are all good practices. And you can't find any rule anywhere in the codes that says do this. But it's important that you understand the big picture. Understand the big picture. So this is the big picture. So once you understand the big picture, it's very easy to do structural analysis, because you know the big picture, you know how to model, you know what is meant by modeling. You know, modeling does not mean creating an architectural view of the structure. Modeling means creating a mathematical model of your structure, creating a mathematical model of your structure. So once you do all this with a simple model, and you can see I have numbered all the pages. I mean, I can actually take photos of all these pages and share it with engineer Kamala so that she can actually make it available to you. But anyway, because we have a video, I mean, all these pages are with you because it's on the video. But I have numbered because it's very easy for me to find, arrange it, and also I can easily refer it. So you can see this is the structure. This is a mathematical model. It is not even 3D, it's 2D. And if you create a mathematical model like this, if you know the section sizes, now we have SAP 2000. Within 15-20 minutes, you can create this. Then you can get the results on spreadsheets. And again, you know, I will not bother to get all these results on spreadsheets. What I do is I'll look at the program, I'll take a snapshot and then mark the bending moments, and then manually. And then what I do is, you know, because I'm interested in only the bending moment at the critical section, so I'll look at the critical sections. I will also look at the wind moments, and I'll select a reasonable value to superimpose, adjust the moments accordingly, and then indicate a typical bending moment diagram for one of these peaks, a typical bending moment. So once I have a typical bending moment diagram for one of these beams, the rest is very easy, because you have now you have bending moment diagram and a shear force diagram. Just provide reinforcement. And at over the support, it's a rectangular section, and you perform moment redistribution, reduce the moments over the support, and you will have a corresponding increase in the moment in the span sections. And anyway, you provide a little extra reinforcement in the span sections so that the crack widths will remain lower, the durability will be higher in the span sections, and if the durability is higher in the span sections, they never fail. Anyway, the beams will not fail at the columns, so you will have a structure designed for 100 years, but easily last beyond 150 years, even 200 years. So you do justice to the client, and then you also look at the concrete technology. The concrete technology is very advanced these days. So you, instead of just saying, I'm going to use 25 megapascal cube strength, just say, I'm going to use 30 or 35 or 40. And not to save a lot of concrete, but by using high strength, we are actually adding a new dimension to our construction industry. That is, if you are doing construction, if you are a contractor, you must improve your quality of construction. And if you are becoming C1 contractor or even above, you must have a team of engineers who understand all these principles well. And then they can actually achieve high quality. And with high quality, you are giving the client might spend about 1%, 2% extra, but client will get a structure that can last 50 to 100 years extra. That's number one. Number two, the client will get a super efficient structure because you have optimized it to the great extent. And how you optimize it to a great extent is, you will not use a typical slab system. You will go for more advanced slab systems, more efficient slab systems, or sometimes pre-stressed concrete slabs, and you do various things. And make this, you come up with a very efficient slab system or even a beam slab system and give the client the economy, not from columns, not from beams, but only from slabs. So if you want to optimize a structure, a building, never ever optimize it from the columns, from the beams. So they are the very critical members of the structure. Failure of a column is a disaster. Failure of the beam is a local failure, but if one beam is failing, there's a chance that there are so many other beams which are marginal. Then again, it's another disaster. Then you have to do FRP treatment on so many beams to restore the extra capacity, which is very expensive. And then, whereas you have a slab, you go for a very efficient beam slab system or a PT slab system, a precast PT slab system, or a in-situ cast PT slab system. You do many things. Absolutely no problem. Absolutely no problem. Why? Because now you are making the slab super efficient and possible lightweight. The moment you make the structure lightweight, the foundation costs will go down. Now we can see we are in a very critical time in our history because supply chains have suddenly collapsed. The materials are very expensive and they are short supply, but still we have solutions. The moment you start going for very efficient systems, advanced systems, and you start using high strength materials because the quantity of cement and the other ingredients like sand, metal might not change very much because when you want super high strength concretes, you reduce the water content by using more efficient admixtures. So the cement content might be the same, but still you might be getting a much higher strength because now we are using much less quantity of water. So basically, high strength concrete does not mean higher amount of cement, it means lesser amount of water. And water is not expensive, but admixtures can become somewhat expensive. But the cost difference even today between 30 megapascal concrete and 40 megapascal concrete is less than 2,000 rupees, less than 2,000 rupees. So which is well within what we can afford. And also by using higher grade concretes, you can reduce the thickness of the member, the quantity. So this 2,000 rupee extra will not be a problem, but because you are using higher strength concrete, it will become very much more workable. And because you are having super workable concrete mixers, you will find the quality of your finishes will be very high. And then you'll also find you need less cover to maintain the durability. So with that, you can go for smaller sections. And finally, you will find by using higher strength materials, you have made a cost saving. So these are all different aspects that I would like you to concentrate. But the most important thing is make sure when you are thinking, think at a time your brain is working. And that is the time where your stomach is empty, brain has got a good rest. And that is early in the morning. So use the rule, early to bed, early to get up. And early to get up can mean getting up at 3 o'clock in the morning and working 2 to 3 hours before you think of getting ready to go to work. And that will help you to become a super efficient engineer. And if you talk to people like Dr. Dhammika Maharaji, they always do that. And they are very concerned about the quantity they eat, and then they are also very much concerned about their sleep. And you can't call them after 9 o'clock because they are not up. Whereas I can easily contact almost all the engineers in Sri Lanka, even at 11 o'clock. So that is not a good thing. And the other important thing is, never expect government to give price at 100 rupees a kilo, and the real price should be 150 to 200, and because that is the viable price to ensure that the farmers can survive. And we like to have farmers who are reasonably rich. We don't want farmers to be poor farmers. So the only way we can do that is be ready to buy rice between 150 to 200. And then again, we don't want a country that is very poor. So get ready to buy petrol at 260 to 300 rupees, because, once you make petrol this price, automatically the demand will come down, and we'll not have any shortage of petrol. Even the diesel has to be something like 150 to 200 rupees a liter, because that is the only price that will make it viable to run the country. And the next thing is the price of electricity. Expect it to be something like, so the electricity cost should be something like 0 to 35, 35 to 70, 75 to 70 to 105, 105 to 140, 140 to 175, 175 to 210. These are the slots. So this can be 10 rupees per unit. This can be 15 rupees per unit. It has to be 20 rupees per unit. This has to be 25 rupees a unit. The whole range, no slots, 30, and this has to be 35 rupees. That is the only way you can run this country, because successive governments have done massive blunders in running the country. And the moment you do that, the people with rooftop solar will think of having, say, 5 kilowatts of solar. You will fix 4 batteries, 400 amp hour batteries, hybrid batteries, and you will also have an inverter, 5 kilowatts. So by 7 a.m., you will have sun rising. At 7 a.m., you go off grid. And then here is you are on your own electricity. This will last until 5 p.m. with solar, and after 5 p.m. you go on battery until 8:30 to 9:30 p.m. And then 9 or whatever this time, 8:30 to 9:30 until 7 p.m. 7 a.m. the following morning, you go on grid. Why? Why do you go on grid? Because now you are ensuring that base load is there, because without base load, you cannot operate 900 megawatt of No11. So the only way you can operate No11 is to have base load on the system. So we like all the customers on the grid during the night time, and we like all the customers off grid during daytime. And that is the solution for this electricity crisis. And if you want, I can give all the details. And if you want, I can even have a separate lecture on that. And so basically, the whole idea is that we have off-grid autonomy. And you'll ask, you are a structural engineer, why you are doing all this? But before I became a structural engineer, I learned motor mechanism from grade 6 to 8. And I learned wiring and all that electrical things as a kid, because we had electricity at our homes. So, and I also did research on energy, on buildings. I have published in that. So I know this, and I also know air conditioning very well. And I also know building services very well. So I have taught that subjects from 1995. And I also know structural engineering. I can design buildings, bridges, and nuclear plants, or anything else. Yes. And I have designed water tanks a lot in 1987. So basically, I'm not just an engineer. I'm an engineer, not a civil engineer or structural engineer. I'm an engineer, so I can come up with many things. And this is one of the solutions that I came up of grid autonomy. And I have gone to Germany to learn this on a study tour. So we have learned all these techniques that they use in Germany. And with that knowledge, I'm telling you, it's possible to go off grid, and we can have grid autonomy. The moment you look at the problem, you can see its ideal solution. The problem is we have the base load here, and 6 hours, 12 hours, 18 hours, and 21 hours. This is the worst. Peak 2,700 megawatts. These peaks will need something like 2,100 megawatts. And then night time we'll have about 1,200 megawatts, because to have a base load of 900, it's good to have something like 1,200 on the system, so that the base load is assured. So what we do is remove all these people from the peaks and assure we have a 900 base load. Almost throughout the day, we have something like other 300 to 500 megawatts on the system. The moment you do that, by helping all the people to go off grid, you can provide these are place where we have the problem. There may be few towns that can be consuming, but all the electricity is consumed here in the Western province. you take Western province with rich people out of the grid. The moment you do that, anybody else in the rest of the country will be contributing only to the base load. And because almost all the factories have rooftop solar, you encourage them also to go off grid. The moment you get rid of all the factories, the moment you get rid of all the houses consuming high quantity of electricity, and also anybody who is not having any roof area but huge consumers like tall buildings, you will encourage them to go for solar farms, so that though they consume a lot of electricity here, they generate a lot from the solar farm, so they compensate for their usage, and with all that, we can solve the electricity crisis. Short term for 2 to 3 years will be okay, but the base load will rise again, so we have to go for LNG in future, because the chances of going for coal is not very. It's okay to go for coal. Absolutely no problem in going for coal. And if we have 1,000 megawatts of coal or 2,000 megawatts of coal in Sri Lanka, still we are at 1 ton per person per year. We are less, but we have USA 17, we have UK 8, we have Germany 9, we have France about, they use a lot of nuclear, so they are about 5, and China 5, India. These are carbon footprints of these countries, 2 to 2.5 range, and Korea about 12, or Middle East 18 to 20, because there is a lot of AC, they have oil. So is it a crime to go for coal in Sri Lanka? No, it's not a crime. Just go for coal. Otherwise, if you don't like coal, go for LNG. Because LNG also has a good future. Because we might find LNG in Mannar Basin shortly. Then anyway, LNG is okay for us. So think about it that way. Long term, short term, there is a solution, go off grid. Go for off grid autonomy. That means we all disconnect from the grid for the daytime, because we have solar and we have batteries to stabilize. We do everything on our own. We don't become a burden to the government. So the government can look after the poor people of the country who can't afford to do all these things. The people who are getting 40,000, 50,000 rupees a month, we can't expect them to do all these things. So the government must look after them. Government should not worry about us who are earning more, who could already afford rooftop solar. So if you can afford it, so what basically, if you have 5 kilowatt, but if you have already installed 10 kilowatt, what you do is you divide it into 3.5, 6.5. For 6.5, use the 10 kilowatt inverter that you already have, feed the grid as you do already. From 3.5, have 2 numbers of 100 amp hour hybrid batteries. And then what you do is you'll have 3.5 inverter and use this to make the house off-grid autonomous. Off-grid autonomous. Make it all off-grid autonomous, and you are off the grid from 7 a.m. until 9 p.m. And by that time you are past all the peaks. You are not a burden to the country. You are not burden to the government. And most importantly, you are not a burden to yourself, because your electricity bill is very small. Why? You are using your own electricity. And So to help this happening, we need the GOSL peoples, POC, and then private banks, so many, and provide a loan at 12% for going up to 350,000 to 500,000, payable over 5 years. And for this, you will pay only about 1,200. 1 million you pay. 100,000 you pay 1,200. So you might pay about 7,000 rupees per month over 5 years. Over 5 years, you might pay only about 7,000 rupees. But the banks will be happy because people are now taking loans at 11 or 12% interest. And this kind of monthly payment is not a burden to you because anyway, your electricity bill will save more than that. And you are not a burden to the country. So within 2 weeks to 1 month, we'll make sure whatever the dollars we have is now spent on bringing batteries. Otherwise, we go to ADB with this kind of proposal. They like that type of proposals and get all batteries high quality from Japan. And we'll organize some kind of concessionary loan payable over 40 years from Japan and buy everything from Japan. And we can think of European Union or something, get another loan and import inverters as a very long-term concessionary loan, not a short-term loan from China, but a long-term loan from EU countries because they manufacture there, so they like to create a big market for their own products. So we bring inverters from Italy or France, and we bring batteries from Japan, and we help, and we can bring solar panels from China because all the solar panels are made in China, but it's not a problem. So we bring it. And again, we can organize some kind of World Bank or ADB package for that. So dollar is not a problem for that. So we can bring all these things the moment government is keen to negotiate and get things done. The moment you have all the people who can afford to get a loan up to 600,000 rupees, loan up to 600,000 rupees from a bank where you will go off grid, you can pay 6,000, 7,000 rupees a month as the loan repayment because your electricity bill has come down from 10,000 rupees to 3,000 rupees. So if you are using AC, otherwise if you are not using AC, it has come down from 7,000 rupees to 1,000 rupees. So you are saving the money, you paid. So the solution is there. So you can see it is fully workable. So with that, I will stop the lecture. And if you want anything, if you want me to conduct a lecture on this, I can bring in more people who are able to do that. And I have already done it at my uncle's house. He's off grid now. And I wanted to do the experiment. So I used, actually, it's not me who asked it. He said, the situation is not good and we might not have enough dollars to bring. He's a very educated person. So he told me, we might not have enough dollars to import fuel for electricity. I have done enough service to this country. I don't want to suffer at my old age. So I want to go off grid. I said, fine, I'll arrange it. I arranged a person who has done NDT at our university, 1 year junior to me, starting 83. I started 82, and he did it very well. Even today, I had a long discussion with him. So he did it very well. And his contact number is Anil. And he does a lot of things. And if you want, you can contact him. His contact number is Contact is not 717677613. Not 717677613. This is phone number. So you can take down his phone number. If you want any information, contact him. On the other hand, if you organize any kind of discussion for us, I can bring him. He will explain A to Z of it, and I also can explain it, and we can have a healthy discussion with our electrical engineers, because we are helping them by reducing their customer base so that they don't have to generate at 80 and sell at 20. At the moment, because they are having too many customers, they are generating at 80, selling at 20. So the moment you take all the customers out of the grid, the system will work, but you have to understand, we cannot be living in a country where everything is based on subsidies, as some political parties like to see. We cannot be doing it, because so basically, if you want to run a country properly, you have to have a good system where everything is run profitably. Every institution is run profitably, so that people will not ask for concessions, but they will actually say, we like to pay more taxes because we can see our taxes are working. So that's the way we have to change our mentality. So don't think that these are prohibitively expensive tariff. The tariff system is to encourage people to go off it, not to stay with the system. The moment you do that, it will be the first country in the world where the people have decided they are going to go off grid, because Sri Lanka is the first and the most ideal country in the world to do that. The reason is, almost every day we have sunlight. It is same with wet zone, dry zone. Wet zone, even if rains, it rains 1 hour, 2 hours, then after that sunlight. Only less than 1 week for the whole year, you have completely dark days. And those days, no harm in staying with the grid, because they are the rainy days of the monsoon season, and those days, anyway, we'll have huge quantity of water in our reservoirs. So the reservoirs can be producing all the water throughout the day, and no harm in all of us staying with the grid. But the chances are, in that kind of rainy days, we'll not use AC. So our loads will be anyway lower. And anyway, we have batteries, so sometimes we might use our battery power to a certain extent, because we like to reduce our electricity bills. So you can see this is a very workable solution, because your electricity bill reduce, more you stay away. So it is a solution system where the consumers are encouraged to stay off grid than staying with the grid. So I have given 2 things. One is, I have told you how to do modeling, how to think, how to adjust your life, and most importantly, how to solve our present crisis, and that is no dollars, no electricity, no petrol, no diesel, and that is because our attitude is wrong. Thank you very much. So, Engineer Kamala, you can actually, we can have.
Thank you. Yeah. Thank you so much. It's a very comprehensive one, and actually there is one question, but I think I'll hand over to.
Our ancient time house structures were analyzed considering lower Mapa is a timber structure, so you don't have to analyze. Okay. Yeah. Lower Mapa is the timber structure on top of stone pillars, and it had a roof also out of copper. So Lower Mapa is a timber structure, so you can easily do it without worrying about it. Yeah. Just common sense will help you all do the load test, do a flow and see how it works. And if you are happy that it's those days, if you don't know how to analyze, you simply load test it. Do a structure and test it. And once you test it with the actual loads coming, then you know how to make it better. And that's the way that most of the engineers, most of the top contractors who are running the things. I know mechanical engineer. I mean, he knows something, but he's so fond of load testing. He gets things right, then he load tests. And I also know another person who has not done engineer. He has a NAB person, in what you call national apprentice, TTI Karnataka type person. He's doing wonders in Sri Lanka. So he gets things right with his own kinds of rules. And then he comes to us and tell, can you produce a good report for what I have done? Then what we do is we produce a report and we optimize it. And today, he's employing over 600 people. And he's having automated machines to make things like towers and export. And he's Mr. Atula Tantri, who is making country trailers, and he can make railway carriages. He can also make trains in Sri Lanka. Unfortunately, we are not asking him to do it. He can make trains in Sri Lanka, and he can use the discarded carriages and converted them to locomotives. So he's so capable. Unfortunately, we are not making use of his talent. And then I know one engineer, he's again mechanical engineer, and we do a lot of joint work, joint research, and we have developed so many new products with him. Again, before he met us, he also used to do a lot of load testing to get things right. And then I know the chairman of Maga Engineering. Anything he's not sure, he will load test. So that's why Maga Engineering is doing so well, because they don't rely too much on engineers. If something is not sure, construct that structure, load test it and see how it behaves. If you are sure that the loads can be taken, and then ask a better engineer, a top engineer, to optimize it further so that you can make a saving. So don't think analysis is the only way of doing things. And that's why when you do research, we don't rely on analysis. We do the experiment, and then we validate the computer software to using the experimental results so that we know our computer method is correct. Then we forget about the load testing. We do a lot of expansion of the methods using computer. So that's the way we do things. So analysis is not necessary. Analysis is there to help us, but if you can't analyze, load test it. Thank you. So, I mean, you are talking about Flocan and all that software, but basically, I don't use any of these software. I will find a bending moment and do a hand calculation, and within 1 second, I will get the answer. And how I get the answer is simple. And what I do is, I will simply find the bending moment, diagram, bending moment, and I'll find MOBD squared, and then the 100 SOBD, in my case, is given by MOBD squared divided by 4 plus 0.05. If it is lightly reinforced, or this quantity will be 0.01, 0.1, 0.1. If it is heavily reinforced. So basically what I have done is there are charts like this. So I have got this part of the chart as this is, if this is x divided by 4 plus 0.05. This part of the chart as I have got a simple equation for this part of the chart, that is x divided by 4 plus 0.1. So I don't do anything. I don't use Procon. I don't use any of these things, but I will not worry about Procon. I'll write my own spreadsheet program and do the design. I will not waste my time with Procon, because they are written by somebody else. Why do you want to use somebody else's program when you can easily write your own program on a spreadsheet? Then you'll be thinking. Otherwise, you are believing what Procon says. Whereas when you write your own program, you know how it works, and you have a simple rule like this to check your answer. So why not use it? So this is how I do designs. And basically, I can design a 100-story building in 3 days, let's say 4 days. I give all the drawings, sketches, and then I give a challenge. I'll give you 3 months. You check my design, all the drawings are there, check it. And if you save it by 5%, if you show you can reduce the cost by 5%, I'll give 50% of my fee, which is 1% of the cost of the structure. And if you show that the structure can be optimized by 10%, I'll give 100% of my fee. And again, that is 1% of the cost of the structure. Not the structure, the whole project, cost of the project, cost of the project. So I don't even need a computer to do the design. I need only a calculator. I'll do all the calculations, give all the drawings, and so basically, I will not waste my time on programs like Procon. I might write a very nice spreadsheet where I can demonstrate all my calculations. On the other hand, I might use MIDAS, get MIDAS to produce all the detailed calculations, and I will use simple calculations to show MIDAS answers are all correct. So I'll do something like that, but it's all up to you. I mean, it's totally up to you. I mean, how you do designs. But my way of doing designs is I have a complete set of rule base, and I can simply convert. I can simply give the reinforced concrete, reinforced drawing. I don't need to even look at code. I don't touch a code when I design, because I have my own rules of design. So that's why I do it, but it's up to you. You can do design whatever the way, because at the end of the day, you have to take, when you put the sign, when you sign, you have to take the responsibility. So knowing that very well, it's up to you to decide how you do the design. So only thing is, keep in mind, if something goes wrong, you can't say, I use this code or that code. You are totally responsible for something that has gone wrong. And because of that reason, please make sure you do a complete risk analysis. So you do a complete risk analysis. And the most important thing is, there are one rule: never do things that you do not understand. And what are things that you don't understand? That is geotechnical. And most of the structural engineers have absolutely no idea of geotechnical. So never do things that you do not understand. And one of the things that you do not understand is geotechnical. So don't become a geotechnical engineer. Don't try to replace the geotechnical engineer. Always hire a geotechnical engineer like Dr. Nalin De Silva. If you have a complicated problem and his number is 0706494973 or 0755494973. Hire a person like that who is a master of the game and get him to tell you, get his comments, pay him something, get his comments, so that never ever think that you can do a geotechnical part of the basement design. Never ever think you can do the geotechnical part of the raft design. Once you get the advice from the geotechnical expert, you can do the structural part of raft design, but always first get the advice from the geotechnical engineer. I have vast experience. I know how to handle geotechnical, but I never do geotechnical, because geotechnical must be done by an expert geotechnical engineer, or else get a person who has done M.Sc in geotechnical engineering and who has done it properly, so that he knows who is a master. Otherwise, go for an expert and get the opinion, then hire, with their opinion, hire one of these engineers to do all the calculations. So the whole system is there. Similarly, don't do hydrological designs and dewatering type of things. Get a hydrological engineer to do that part, and ensure you do only structural engineering But of course, you can have a good knowledge, but hire these other professionals to do specific jobs that they are real masters. But you can be a real expert on this area, doesn't matter. But unless you have done MSc or something, in every area that you can think of, hire an engineer who has vast experience. And so basically, with that, I'll conclude. Engineer Kamala, what do you think? Is it okay?
Yeah, finished actually. We are going to finish it. Thank you. I invite Engineer Trima to do what. Thanks.
Yeah, thank you, madam. Good evening, everyone. So I'm Trimavitan. I'm fellow member of ISL and a member of Civil Engineering Sectional Committee as well. So I would like to take this opportunity to, on behalf of all of us, to give a vote of thanks, especially for Professor Jayasinghe. Actually, it's wonderful and highly appreciated, sir. You are always sharing your knowledge, your the broad knowledge, and not only that, so you are sharing your general knowledge as well. You are encouraging people in so many areas. Thank you very much. Thank you. Excellent your attempts, sir. So we highly appreciate. And secondly, so I would like to thank the ISL for hosting this event, and also the organizing committee so for the organizing this event. So wonderful event. And so finally, the participants who participated for this lecture, and without you, actually we can't make this event success. And thank you very much for all of who are not mentioned by myself. I'm sorry if I miss anyone. So thank you everyone, and so enjoy your the rest of the day, and so we'll meet once again in another event. Thank you, Professor Jayasinghe, once again.